Good morning. Time for momentum number 2. So we're going to compute some momentums, and we're also going to go ahead and show how to solve some collision problems. Alrighty, so computing momentum. The recipe for momentum is mass times velocity, and as mentioned before, this is a vector. We'll have to consider its direction, but for just purposes of computing things, we're going to compute the absolute value, so we're not going to worry about direction. I'm also going to remind you that kinetic energy is a similar recipe, 1/2 mv squared. And we're going to go ahead and compute the momentum of some objects. And so we're going to need their mass, and we're going to need their velocity. After which we'll compute their momentum and their kinetic energy. All right, so let's start with something pretty obvious. Let's start with a person. And this person is going to be running. This person's going to have a mass of 75 kilograms. And a velocity of 8 meters per second. That's pretty fast running. That's, track star type running. Second thing we're going to do is we're going to do a car. And cars have a much larger mass, let's say about 2,000 kilograms. And they drive a little faster, so let's give them a 20 meter per second velocity. And finally, let's do something a little heavier. No, let's do a baseball. Baseball is fast, but it's not very heavy. In fact, it's not even a full kilogram. I believe it's about 0.6 of a kilogram. And but you can throw it faster than maybe a car can drive. Let's see, 65 miles an hour is 30 meters per second. So let's do that. Let's do 30 meters per second. Okay, time for us to get the calculator out and find the momentum and kinetic energy of these various things. Momentum is fairly simple. Because it's simply the product of the mass and velocity. So let's start with the person, 75 kilograms times 8 meters per second. A big old 600. Now, interesting point, 600 what? What are the units of momentum? Well, the units of momentum are the units of mass, which are kilograms, times the units of velocity, which are meters per second. So it certainly could go together to say kilograms times meters all divided by seconds. And some people do that, and that is an appropriate unit for momentum. But remember, when we have lots of these kilograms, meters, and seconds together, sometimes we sweep them together and give them a name. And so if this was kilograms, meters per second squared, that would have been a Newton. So the fact is, it's just a little off of a Newton. So this is actually the same as a Newton times a second. And since this is a little shorter, this tends to be the unit used for momentum, Newton seconds. I would petition to get it named the Harmon, but I arrived on the scene a little too late to be honored for research involving momentum, since it was done at the time of Isaac Newton. Okay, let's work back on the car. 2,000 times 20 equals, okay, that's not what I wanted. I don't think that's right. 2,000 times 20, and that's 40,000 Newton seconds. But that's a lot more than the person. So yes, if a person collided with a car, the car's momentum would dominate the situation. I think we all know that. And then baseball. Let's see about the baseball. We have 0.6 times 30 equals, and that's only 18 Newton seconds, which means, I guess, if you threw a baseball at a person that was running towards you, it wouldn't be enough momentum to stop them. I'm sure it would hurt, though. Maybe get that going for you. All right, let's finish the job and let's find the kinetic energy of these things. So 0.5 times 75 times 8 squared. This is going to be 2,400 joules. Okay, so there's no reason to compare these two numbers because they're two totally different things. But what we should do is we should keep track of the changes. All right, so look at things vertically, not horizontally. All right, the car is 0.5 times 2,000 times 20 squared. Whoa, okay, 400,000 joules. And the baseball is 0.5 times 0.6 times 30 squared, which is 270. So here we change from 600 to 40,000. That means that we're in the hundreds place, and we move 2 places over to the tens of thousands place in the jump of the momentum, and that's mainly because the mass of the car is so much more. But here we do roughly the same thing. We jump from the thousands place to the hundreds of thousands place. But I think it's an even bigger jump, and the reason is that this was a 6 in the hundreds place going to a 4 in the tens of thousands place. This is a 2 in the thousands place going to a 4. So it is a significant jump, and I think that is borne out because the velocity increases by more than than we would think. Here, comparing the person to the baseball. This baseball is, I would say, how many times? If this was 20, you'd have to do that 5 times 6, so about 30. This is 30 times less than that. And this number is only about 10, less than 10 times less than that. So that means that the high speed of the baseball is really making the energy swoop up to be a lot larger as compared to the momentum than it was in the case of the person. All right, so that's a basic calculational thing. Let's now talk about the impulse momentum theorem. Let's get this out of the way. The impulse momentum theorem is an interesting facet. The impulse momentum theorem says that a force acting for some time can change momentum. And it basically looks like this. A change of momentum occurs when you have a force acting for a certain amount of time. Now, I didn't used to put the delta in front of time, but because I put the delta in front of time, you can read this as AP is fat. And that is something that we use in this class to help us remember the impulse momentum theorem. Now, why do we need an impulse momentum theorem? Remember, momentum is a conserved quantity. That means in a closed system, the total momentum is constant. Ooh, maybe we should write that down too. That makes it sound like momentum can never change, but that's not true. It's the total momentum that's constant. So momentum can be transferred from one thing to another. And this is the amount of the transfer. This is the change in momentum for any individual object that's involved in a closed system. So, let's see what we can say. So this part right here, this is called the impulse, and it causes a change in momentum. And I want to point out that this is very similar to something we had back in the chapter on work and energy. We said that you could have a change in your kinetic energy if you did work, and work was a force times a displacement. Look at the similarities. First of all, of course, the major similarity that that momentum and kinetic energy have with each other, and they're on this side of the equation. And then on this side of the equation, it's a force, but in this case, it's acting for a certain amount of time, and in this case, it's acting over a certain distance. So that's why energy is not good at helping you solve for the time, because it's not in the equations. But momentum will be great for helping you solve for the time. Momentum's not so great at helping you solve for the distance because it's not in the equations, but energy is great at helping you solve. Now, I'm not going to say too much more about this impulse because it's a really simple concept. You just take the force and multiply by the duration of that force, and there's your impulse. So if the word impulse appears in the equation or in the problem, then you're going to be using the impulse momentum theorem. And now let's get to solving some problems involving collisions. These are going to be problems that use conservation of momentum. So let's start with a situation. This is going to be a perfectly inelastic collision. And as you recall, perfectly inelastic means that they stick together. And to illustrate this, we're going to have a train track, and we're going to have one boxcar on the train track. This boxcar is going to have a mass of 1,000 units. I don't know if it's kilograms or whatever, but that's 1,000 kilograms. And a velocity of 3 meters per second. That's a little faster than walking speed. That's trotting speed. And it's got one of those little claws on the front, the ones that lock to the claw on the other side, which is another boxcar. And this boxcar is also 1,000 kilograms. Let's say that's the mass of an empty boxcar. This one, however, is going to be at rest. Now, at some point, they're going to collide, and then they're going to lock together and move off together. So let me draw two boxcars that have locked together, and they're moving off together. And I'd like to know, what is their velocity? Now, let's label this boxcar 1 and this boxcar 2. Now, when they're mated together, we can call that object, I don't know, 1, 2. There you go. It's like that's like Brangelina or whatever those celebrity names are. All right, I want to show you how to solve these problems. Now, this little jaggedy line means something happens. So we have a before and we have an after, okay? And it's customary on the after side to put a little accent mark, a prime mark, V prime. And that prime mark just means after the collision has happened. Okay, so what you do is on this side of the little jaggedy line that means something happened, before, after, something happens in the middle, write down P total. That is the total momentum for this situation. It will be equal to, right, put the equal sign right underneath the jaggedy line, P total prime. Why prime? Because it has to do with after the collision. Now, the total momentum before the collision is made up of the momentum of car number 1 plus the momentum of car number 2. Afterwards, the total momentum is made up of the car number 1, 2. You can put a prime on that if you'd like to. Let's do it. Let's keep ourselves honest. So the total momentum before equals the total momentum afterwards. That is a mathematical statement that is equivalent to the law of conservation of momentum. Now we're being more specific to this problem. There are two objects ahead of time, so two momentums have to be added together. There is one object afterwards, so only one momentum afterwards. Now, each of these momentums needs to be replaced with a mass times the velocity. So the mass of 1 times velocity 1 plus the mass of 2 times velocity 2. That replaces these two momenta. And over here, it is the mass of 1 plus the mass of 2. That's the mass of the combined car. We don't lose any mass. Times V prime. We could put a subscript 1, 2, but I think it's pretty unambiguous. After the collision, there's only one object. So just saying V prime is pretty unambiguous. Now it's time to put the numbers in. We have a mass of 1,000 and a velocity of 3, plus a mass of 1,000 and a velocity of 0, equaling a mass of 2,000. Oh, and now I decide to put it in parentheses. I guess I have to because I have a naked variable over here. So maybe everything should be in parentheses just to make this fair. But there you go. Okay, so this is 3,000 plus 0 equals 2,000 V prime. Now, you might have said, Harmon, look, I knew this car wasn't moving. I knew I was going to put a 0 here. Can I just leave this off? Yeah, when you get better at this, you can just leave that off, all right? But for learning purposes, let's be very careful. Let's make sure that the math tells us what to do and that we don't make any mistakes. So let's shorten this up so we can do this. 3,000 equals 2,000 V prime. I mean, you could divide through by 1,000 and get rid of some zeros, but we could also just say, hey, 3,000 divided by 2,000 equals V prime. Well, that's 3 halves, so that's 1.5 meters per second. We now know that the combined car will be moving with 1.5 meters per second. Many of you could see this coming. Many of you could see it coming because this car is going at 3 meters per second, and it's going to run into something that's of equal mass. And now we have a double mass object, so we're going to have half the velocity. Yep. Those are good instincts. So let's change this up a little bit, shall we? Let's see. We're going to need to cross the whole page. There we go. So we got the box car coming in. Only this one's going to be loaded. It's 2,000 with a velocity of 3 meters per second. And it is going to hit the old 1,000 resting box car resting boxcar face. And then they're going to stick together. I should get better at writing these stuck together or drawing these stuck together things. There we go. And this is moving. This is going to be moving. And I want to know how fast it's moving. Boxcar 1, boxcar 2, boxcar 1, 2. All right, let's go a little faster. We always write P total equals P total prime. Beforehand, there are two objects, so P1 plus P2. Afterwards, P1, 2 after the collision. Now, M times V, M1 V1 plus M2 V2 equals M1 plus M2 times V prime. Notice that I'm moving away so that I can keep the equal sign under the zigzag. It's just a nice visual way to see this, at least until you get the numbers into it, and then you're doing algebra. So now we have 2,000 times 3 plus 0. That will be 0 because its velocity was 0 equals, and this is now 3,000 V prime. So 6,000 equals 3,000 V prime, and 6 over 3 equals V prime equals 2. Well, that's interesting. Heavier boxcar moving at the same speed as our previous example hits the same resting boxcar, and then they move off at, well, 2/3 of the original speed. And that's because this had more momentum because it had more mass. So there's more momentum to share. And when it shares it between an object that's actually a little heavier. So this all works out. Okay, let's do one more on this vein because we're here. One more perfectly inelastic collision, only this time we're going to have both objects moving. Somebody's going to get cute, and they're going to take the 2,000 kilogram boxcar going at 3 meters per second, and they're going to have another boxcar that happens to be moving. This is a 1,000 kilogram boxcar, and it's going at minus 2 meters per second. All right, this shouldn't happen in a rail yard, but there you go. They're going to lock together. And I would like to know, what is the velocity afterwards? And it's also not clear which way they're going to be moving, right? We have some momentum this way and some momentum this way, and we got to figure out which way they're going to be moving after they lock together. I think many of you can tell from the first picture that this car has more momentum because it has more velocity and more mass than this car. So the momentum to the right is probably going to win out over the momentum to the left. But let's let the math show us so that you have faith in the process. P total equals P total prime. P1 plus P2 equals P1, 2 after. Okay, training wheels. Let's say you want to skip this step and move right to the next step because you know what's going to happen. Be my guest once you get good at it. But if you're not so good at it, write stuff down. Ink is cheap. Plus, it looks impressive. And remember, we have to have the minus sign on this velocity. Momentum is a vector, and direction is important. We might have glossed over minus signs when we were doing kinetic energy, but that's because they were going to get squared away anyway. So, but here we have to be very careful about that. Okay, 2,000 times positive 3 plus 1,000 times negative 2 equals 3,000 times v squared. So 6,000 positive minus 2,000 negative equals 3,000 v prime. So 4,000 equals 3,000 v prime. And 4 over 3 equals v prime, which is 1.33 meters per second, which tells us two things. Tells us when they lock together, they're going to be slower than anything else we've done so far with momentum. But it also is a positive number, meaning that these cars will be moving to the right. They'll be moving that way. The momentum to the right won out over the momentum to the left in this collision. All right, there's one more type of collision I'd like to talk about, and I know I'm going to go over my informal 20-minute limit here, but it works out. This is a very special, perfectly elastic collision called recoil. And recoil is a kind of collision in reverse, okay? When we think of recoil, we think of guns and stuff. So I'm going to draw a picture of a pistol. This is a really lame picture of a pistol. And this pistol is going to have a mass of 2 kilograms. I don't know if that's reasonable. 4 pounds, that sounds about right. Inside the pistol is a bullet. And the mass of the bullet, okay, so this is going to be the mass of the gun. This is going to be the mass of the bullet. Mass of the bullet is going to be very small, 0.02 kilograms, okay? And what's going to happen is in the beginning situation, the bullet and the gun are at rest together. Then somebody pulls the trigger. What happens? Well, the gun minus the bullet will recoil this way at the velocity of the gun after the collision. The bullet comes out this way, going very fast, and I'm going to tell you what fast is. Excuse me, fast is going to be 400 meters per second. So this is a collision, but it's a collision in reverse. Instead of coming together and stopping, these are stopped and then they spread apart. And we don't even need to know the magic of how gunpowder works. It's part of this line. Something happened. We have before, we have after. Okay, let's do it. P total equals P total prime. That means that the momentum of the gun plus the momentum of the bullet equals the momentum of the gun afterwards plus the momentum of the bullet afterwards. Sorry, my P's are looking a little bit like flags now. I'll try to work on that. The momentum of the gun, 0. The momentum of the bullet, 0. These are beforehand. Neither one of these is moving. So no matter how you slice it, the momentum is going to be 0. But here, we need the mass of the gun times the velocity of the gun afterwards plus the mass of the bullet times the velocity of the bullet afterwards. And I apologize, my pen is bleeding ink into the paper and making these B's look kind of like blobs, but I'm here narrating, so I'm cool with it. All right, so 0 on this side. Mass of the gun is 2 kilograms. Velocity of the gun afterwards we don't know, so we'll leave it as a variable. Mass of the bullet is 0.02 kilograms, and the velocity of the bullet afterwards is 400. Positive 400, I'm still taking positive to be this way. Okay, so I guess we need to go a little further. 0 equals 2 VG prime plus. Now, what is 0.02 times 400? Now, I want you to know I could probably do this in my head, but I don't want to make a mistake on camera. That's 8. Okay, that 8 needs to come to the other side. Minus 8 equals 2 VG prime. That means that minus 4 equals VG prime. That's minus 4 meters per second. That means that the gun will recoil in the negative direction, and it will recoil at 4 meters per second. Now, 4 meters per second, like I said, is a reasonable velocity. That's like a running person. And that's why when you shoot a gun, you have to deal with the fact that the gun is going to come back at you. It's often easier to reduce this velocity by simply making the gun heavier, either actually physically making the gun heavier, or by holding it really tightly in your hands and making your body's mass part of the gun's mass. And if that mass is larger, then this recoil velocity is actually less. So if you ever get an opportunity to fire a gun, make sure you hold it tightly. Unlike a 12-year-old Mr. Harmon did when he went shooting shotguns with his grandfather and was having trouble aiming the shotgun at the clay pigeons. And so I moved it away from my shoulder a little bit to be able to look down the barrel. And then I pulled the trigger and that fell on my keister. That was not a good moment for me. Although the family thought it was hilarious. Okay, that's how to solve momentum problems. We'll do some more of that in homework and in class, but that gives you a pretty good idea.